Hello, everybody, and welcome to our webinar on new fiber connectivity options inside the switch chassis. So, whether you are anticipating a major redesign in next generation of switches or in the generation after that or the one after that, what is clear is that greater bandwidth, lower system power per bit, and better thermal management will be key parts of the design inside the switching chassis. And so hence there's the need for fiber inside the chassis. And when we think about it, the number of fibers that will be in there will be a very large amount. It could be dozens, it could be hundreds, maybe even over 1,000 different fibers. So in this 1-hour webinar, we will hear first from Paul Yip, who will discuss an innovative fiber shuffle solution from Optec. The idea is to facilitate that fiber management and system redundancy from the CPO optical engines. Right after Paul, we'll hear from Fujikura's Teruhiko Omori, who will present the various types of fiber suitable for these applications. This is the 14th in a series of webinars that have been presented by COBO, the Consortium for Onboard Optics, and sponsored by DuPont Silicon Valley Technology Center. A replay of the webinar will be available in about a week, and the presentations that you're about to see, the slide decks themselves, are already available on the COBO website. After the presentations, we should have plenty of time for questions. You are welcome and encouraged to submit your questions using the Q&A function that you see below. I'll read the questions out after the presentations. I'll do so anonymously. So please ask away. And if you could please indicate whether the question is directed at Paul or at Omori-san. Thank you. So with that, let's kick it off. Let's get started. Paul, the floor is all yours.
Hi, everyone. This is Paul from Optec. Yep. So I'm from the product marketing team of Optec. Yes, it's an honor to give the presentation for today. Yep. So let's get started with the design consideration on the fiber management inside the data center chassis. Yeah. So we see the CPO trend is coming, and we want to move fiber inside the chassis. There are a lot of room for fiber management inside. Yeah, so we would like to propose the flexi circuit fiber shuffles. Yeah, and hopefully that's one of the enablers of the CPO switches and also other systems going forward. Yeah, so Optec has been in the industry for over 20 years. Yeah, we've been making fiber optic cable assemblies and also interconnection solutions. Yeah, so we've been a COBO member since 2017. Yeah, so let's get started with the riddle. Yeah, so just to wake everyone up. Okay, so can we connect A to A, B to B, and C to C without crossing the line? Yeah, I'll have the answers shown after the presentation. Yeah, so this is my favorite diagram here from the IET optoelectron. It explains the idea how the pluggables are first used in the switches, and eventually the fiber go inside on the board through COBO connectors, optical engines, even the chipsets on the optical I/O, and finally is going inside the chipset chips with through the interposer. So we see a lot of fibers inside. Yeah, so we're talking hundreds to thousands of fibers within the 1U box. Yeah, so the amount of fibers are massive. Yeah, so how can we deal with that? Yeah, so just another diagram to show from the top view. This is the chipset. Yeah, and connected by COBO OE chipset and going directly into the ASICs. Yeah, fibers are here. So it goes to the I/O of the either OE or ASICs. Yeah, so this is not the focus for today, but from this I/O, you can have an option to go directly to the front faceplate, or we can go through a midboard to have the fiber managed a little bit better. Yeah, and to give a lot of other advantages. Yeah, so from here, we are proposing to use this flexi circuit. Yeah, so I will explain a little bit more about this later on. Yeah, but mainly speaking, we are talking about midboard. This is the I/O interface, and this is the faceplate interface. Of course, there are also external light source to be coupled so that the extra light power is given to the ASICs so that it can go outside to the outside world. So there are PM fibers used inside. With conventional patching, yeah. So you see, we can. This is just an example to use a multi-fiber connector, breaking out into LC or duplex connectors, and then do a little bit of a crossover, patch them together again, and going back into an MPO to the next level switch. Yeah, from this, we can see there are several layers or connectors in the optical link. Yeah, so that's the optical penalty that we need to build in the link. Yeah, so we see there are room to improve that, and also it takes up a lot of spaces. Yeah, so the question is, can we put all these cables inside the chassis, which is like a 1U form factor? Would there be too many cables? Yeah, so the answer is yes for us. Yeah, so the fiber shuffle is basically rearrange these fibers so that it connects to the OE inside, and then going out from the face plate I/O. So mainly it can facilitate two things. One is fiber mapping. The other one is OE redundancy. And after this, we can see a lot more simplified cabling at the data center. Yeah, so it can go directly or into the next level switch. Yeah, so all these channelings are pre-built or fabricated and tested at the factory. So it's like you can just plug and play this kind of switch. And of course, we need to test or calibrate the whole network. Yeah, but it's making life much more simple. And it also saves the OpEx because if we manage the cabling, it will consume a lot of time as well. Yeah, so the fiber shuffle, yeah. The idea is to bring the fiber from one port, I call that the original port, yeah, to the destination port. Yeah, and in the middle, we can rearrange this fiber so that it can connect from multi-port to multi-port. Yeah, so, and it can also go into different directions as we need. Yeah, so, and then the connectors can be in different types of connectors. Yeah, just to facilitate different bits in the midboard or in the faceplate, even on the external light source. Yeah, so these are other kind of fiber shuffles on top of our flexi circuit. We can also use a box to hold all these fibers, or we can minimize the fiber count to put them inside a miniature. So it's a pretty flexible solution. So I would like to go through a little bit more about fiber mapping. Yeah, so if we look at the OE, typically we are seeing, for example, 32 fiber N per RX and TX. Yeah, so from this midboard, we can break out all these fibers to 4 different connectors going to the faceplate. So if it is 3.2 terabyte OE. Each of these connector will get 800 gigabyte. So yeah, the bigger granularity is transferred into a smaller granularity, and it's always good for reliability concerns. And also, we can see if one port fails, other 3 ports is still connected with the OE. So this is the fiber map. About the redundancy, so we can see, for example, we can connect one fiber end at the faceplate to 4 different OEs. So if one OE fails, we can still have 3 other OEs available. So we see this as a very good advantage. And of course, it's not a must to build it like this. But it can build like this. And with the fiber shuffle, it's a little bit more easier to design the switches going forward. So this is a fiber mesh. Again, it is schematic. So we are talking about 16 OEs in this case, 32 fiber ends at the optic or at the OE IOs, and then 64 connectors on the front panel. So we can see there are total in this scenario 1,024 fibers inside the chassis, 64 connectors in the front panel. So we see the other advantage of this is to facilitate the high density faceplate applications. So with the fiber routing concerns inside the chassis, of course, we know the space is very limited, and the cable congestions will come up if we use large cables. So how can we do that in order not just to manage those fibers, but also improve airflows, because as we all know, heat is the most challenge for every data center. And it causes a lot of power consumptions as well. So hopefully the flexi circuit can help with that. So when we design the fiber routing, we take into account many concerns. But I have another chart to go through that later on. But typically we would like to also think about the reliability, like temperature and vibration inside the application. And the form of routing, of course, so we make them at a factory level in passive ways. So when we assemble all other active components, is it easy for the next level assembly maker to do the operations? So we also take this into account on our fiber shuffle designs. So just to give another idea about flexi circuits, so apart from fiber shuffle where we cross the fibers, flexi circuit is a thin film hold all these fibers onto one layer. And it can exit on ribbons or tubings, to whatever kind of application allows. So typically, we are saying that fibers are intersecting on the thin film, so that it is managed in a proper way and control the bending radius just to make sure there are no extra loss because of the bending radius is put inside the link. So once this is made, it can be stacked up so that we can, for example, 200 fibers per layers, and 5 layers, it will give 1,000 fibers. So it's a very flexible way to plan it. This is an example of our demo kit we put up in the ECOC show, collaborated with US Connect. Yeah, so in this example, it is 1,024 fibers on the blue and the yellow fibers. Yeah, and then there are 128 fibers in red. Those are PM fibers going into the ELS, the external laser source. Yeah, so in this shuffle, it's showing 1,152 fibers in total. Yeah, and of course, this is schematic. So we put everything on 5 layers in total. Yeah, and we chain all this up. Yeah, so yeah, the fiber mapping is already built in. Yeah, so we can see these connectors are connected to different nodes here. So flexi circuit and fiber shuffles are scalable in the production. Yeah, so we've been developing since around 10 years ago, and also, of course, the industry has a lot more history about this technology. Yeah, so for Optec, we have been developing our own semi-automated machines to do the fiber routing. Yeah, just to control better on the polarity. Yeah, so we have also developed the automation fiber laying machines. Yes, so these fiber can be put on this, the thin film without any manual process. Yeah, and the precision is very good. Yeah. So the consideration of the fiber shuffle, I can break out to 5 different concerns. So the midboard interface, the front panel interface, the fiber type to be chosen, the fiber counts inside, yeah, what kind of bending radius is that need to be, yeah, and how much space do we have so that it might influence the fiber type that we are choosing. And of course, we have other reduced cladding fibers to choose in a long-term development. So this is available in the market as well. Yeah, so we can think about the shuffle locations. Yeah, where do we put the shuffles? Is it on the front, on the side, or in the middle? Yeah, we can think about it. Yeah, and how they are mounted onto the PCB. Yeah, so typically we are seeing that on the PCB, there are a lot of SMT components. Yeah, that might, our shuffle can, or flexi circuit can route this around so that we can avoid those bumps on the PCB. Yeah. So, and other concerns, as I mentioned, like temperature, vibration, yeah, and a different kind of cooling methods. Yeah, so we can consider all this in our designs. And of course, finally is how we can service them when one end or one fiber is failed. So just a little bit of fiber introduction here. So I know for CPO applications, it's more single mode fiber using in the market right now. Yeah, so we can choose from various type of cores. I'm sorry, I mean the claddings, so that it gives a smaller and smaller fiber OD, which is higher and higher density. Yeah, so fiber modes, yeah, except the single mode fibers. Yeah, so this is also friendly for multi-mode fiber. So if there is a system that uses multi-mode fiber, no matter switch or other application, it can do the same work as well. So we put this bending radius in mind when we design these shuffles. So in terms of connectors, going into the face plate or on the midboard, yeah, we can choose from three major kinds of connectors. So first is physical contact. Yeah, we are all very familiar with the LC and MPO, these conventional connectors. Yeah, and very small form factors. Yeah, so Omori-san will give more presentation on this later on. Yeah, so the second part is the air gap. Yeah, so AMT by Senko can facilitate this. Yeah, and also other brands in the market is also available. Yeah, so expanded beam. Yeah, so we see US Connect's MXC connectors has a long history, and also the single mode is coming. Yeah, on the other hand, we have Senko's SNEB connectors, yeah, available in the market. Yeah, so yeah, we're considering the density, what kind of performance it can give, and of course the fiber counts here. Yeah, so yeah, in the long-term future, because we know that dust contamination is the biggest challenge inside the data center maintenance or operations. Yeah, so can we use some of the expanded beam or air gap connector in the future? Yeah, it's open, and of course, for some scenarios we can use the blind May as well to make our design better and a little bit more easy for the operations. Yeah, so we can also do this in the shuffle. Yeah, so this is another demo could be shown in the ECOG. Yeah, where we used 200 micron cladding fibers. Yeah, so the main idea is because the connector here is using this kind of fiber, and also it can give us less space, use a little bit more fiber inside the very small base here. Yeah, just to make the shuffle smaller and smaller, and to avoid those SMTs on the PCB. Yeah, so and different from the previous demo, yeah, we make this flexi circuit on the side, yeah, so that it's easier to promote the airflows in the whole module, and yeah, to avoid those SMT in the middle. Yep. So yeah, fiber shuffles can be used in a lot of other applications. These are just some example. Yeah, like an optical backplane. Yeah, you can think of a rack holding a few thousands of fibers. Yeah, and yeah, board to card. Yeah, or actually, is the fiber is on the card. Yeah, connected to the backplane. We can do this as well using the flexi circuit fiber shuffles. And yeah, chip to chips. Yeah, so the good thing about co-packaged optics is getting size smaller and smaller. So can we use one or more chips in the future on one PCB or in one system? Yeah, so it can flexi circuit hopefully is enabling all these kind of designs in the future. So at the start we have a riddle. Yeah, so these are some of the solutions. Yeah, so actually there are many answers to that. Yeah, the thing we're showing here is that if we can get more idea about the design that we're working around, yeah, we can provide a better solutions. Like if we give a shortest link, or we can use the same orientation for the connectors here, or if we would like to have the same length or same length, yeah, we can also plan these ahead. Yeah, so yeah, work with your designers or the module or flexi circuit suppliers. in an earlier stage of the development so that we can make this all happen. So thank you very much. I'll pass it over to Jim. Thank you.
Okay, thank you. And now we'll hear from Teruhiko Omori-san.
I'm Teruhiko Omori, manager at the Optical Component Division of Fujikura Limited. Today, I'm talking about high-density fiber connection with very small form factor connector for over 51.2 terabps co-packaged optics. Yeah. This slide shows today's agenda. First, demand of high-density fiber connection for CPO. Second, MDC and MMC, a very small form factor connector. And third, characteristics of MMC connector. Fourth, applications, reduced cladding fiber and MMC junior. And finally, summary. Yeah. First, I talk about the demand of high-density fiber connection for CPO. This is a decade of switch silicon, SerDes, and parallel optics. Due to relentless advancement between 2010 and 2022, switch silicon bandwidth increased by 80 times from this to here. Optics bandwidth increased by 10 times from 40 gig to 400 gig. And fiber or wavelengths increased per switch by 8 times. This slide shows front panel density considerations for 51.2 terabit CPO switch. Right side shows the DR format with 1024 fibers, and considering external laser source space, MPO 16 and connector is not enough for the front panel. But if we utilize VSFF connectors such as MMC 16 connectors, you can place the appropriate connector number on the faceplate. Next, this slide shows a summary of fiber density per 1 RU and versus fiber granularity per connector. This is conventional connectors, for example, MPO 12, MPO 16, and MPO 24. And this is MMC 16, MMC 24, and MMC 32. Actually, MMC connector has a 3 times cabling port density over the MPO format. Next, I will introduce MDC and MMC connectors, a very small form factor connector. These are the VSFF connectors. Left side connector is MDC connector, mini duplex connector. And the right side connector is a mini multi-fiber connector we call MMC connector. This connector has a same body side and put empty failure inside. I will explain about MDC connector. This is a MDC connector, and this connector has some direct connectable boot for easy connector insertion and removal. And failure has APC polishing support for single mode and multi-mode fiber for the better return loss. And this connector holds maximum 2.0 millimeter optical cable outer diameter. And also this connector has features with easy polarity conversion. Just drop the boot and flip the boots. And also this connector has 3 times cabling port density over the duplex LC connector. This is MDC connector interface, and this is the duplex LC interfaces. And this connector is specified as one of optical interface by QSFPPDD, SFPDD, and OSFP MSA, and complied with IEC standard insertion loss grade B performance, maximum insertion value 0.25 decibel at 90% fiber. And also compliant with Telcordia GR326 and TIA 568. Also, connector cleaner, for example, One Click brand or IBC brand connector cleaner are available in the market. This MDC connector has been already in the market. Next, I'm talking about MMC connector. Basically, this connector is very similar to the MDC connector. Housing shape is same, but slightly different. And this has some elliptical guide pins here, and there is a guide for connection, and APC polishing support for single mode and multi-mode fiber, and the optical cable outer diameter is 2.5 millimeter at maximum. And this MMC connector has a TMT failure, a tiny MT failure, and this has same guide. This connector has a same guide pin hole diameter with emptied one, and also pitch also is the same. So this connector has a utilize a proven conventional MT mechanical and fiber alignment structure, and also compatible with standard 250 micron outer diameter and pitch optical fibers. This shows the interface of MMC connector and MPO connector. MMC connector has a 3 times cable port density over the MPO format. And this connector also has a low insertion loss industry's de facto standard IEC grade B performance and compliant with Telcordia GR 1435. Actually, MMC connector is still under development, but we will test all the performance for GR 1435 finally. Actually, this is similar to MDC connector. So standard cabling industry infrastructure, such as pressure, some measurement system, cleaner, and so on, supports this connector ecosystem. And this is the end phase of MPO and MMC connector. For example, this is a conventional MPO 16 connector, and this is MMC 16 connector. And actually, this MMC connector has a 0.5. Both connectors has a 0.55 millimeter guide beam flow and with 5.3 millimeter pitch and intermatable with these connectors. And also for 24 fiber MMC and MPO connector has a 0.7 millimeter guide pin hole and with 4.6 millimeter pitch. So actually MMC connector is designed to be fully compatible with the MPO format. Next, I will talk about more detail of the MTFEW. This is a conventional MTFEW, and this is a tiny MTFEW. So thickness, length, and height is approximately a half. And TMT failure also utilize the proven alignment structure of MT16 and intermateability with MT16 technology. And standard fiber count and pitch is 16 and with 250 micron pitch. And this is the strong point of key features. TMT failure is compatible with 250 micron and 200 micron and 165 micron fibers. Of course, the 165 micron fiber has 80 micron clad fiber. And this will support backward compatibility and forward compatibility of the cabling solution. And this TMT failure is ideal for onboard fiber management as well as transceivers and hardened connector embodiments. Next, I talk about characteristics of MMC connector. This is this slide shows insertion loss performance. Actually, insertion loss average is 0.11 decibel and maximum 2.4 decibel, and 97% value is 0.23 decibel, and this meets IEC grade B performance, and the returns also good results. And this slide shows environmental testing, thermal cycling tests based on the Telcordia GR 1435. And this result shows a good performance from the view of environmental testing. And also in the market, cleanliness of optical fiber is very important, and MMC cleaner will be available in the market. This is MPO cleaner, and this is MMC connector. And MMC connector has a thinner nozzle and thinner and longer nozzle. And this cleaner can clean the connector for the high density MMC connector. And also, this is a mechanical testing results. We did vibration, flex, twist, and transmission with applied load, and the impact and durability. And based on the Telcordia 1435, and we got good results. And when we take a durability test, we use MMC cleaners, and this shows a good result with maximum increase 0.07 decibel. So this MMC connector, also, MMC cleaner, clean the interface of MMC connectors. Then also, from the view of intermateability, this is very important. We are collaborate with US Connect, and both companies molding fuel and exchange the fuel, and both companies assemble and polish the connector, then measure the insertion loss and return loss for random mating. This slide shows the intermateability results, and average insertion loss average is 0.13 decibel, maximal 0.29 decibel, and 97% value is 0.22 decibel. And intermateability result is similar to IEC grade B performance. Then also we are developing 24 fiber MMC connector. Basically, MMC connector, the standard is 16 fiber, but we sometimes the market needs a 24 fiber connector. So we are developing this connector, and this result shows a 0.1 average insertion loss is 0.13 decibel, maximum 0.34 decibel, and 97% value is 0.28 decibel. Slightly worse than IC grade B performance, but we will complete the development of 24 fiber MMC connector in the future. Next, I will talk about applications, reduced cladding fiber and MMC Junior. This is a MMC Junior connector, and this side, there is a MMC connector, and inside the box, we will apply MMC Junior and MMC Junior connector has compact housing, and you can insert into the adapter. And also in the market, sometimes customers want to insert a connector at the same time. So we have a ganged or a bundled MMC connector. And this slide shows reduced cladding applications. MTFL-based connector interface compatibility between conventional 125 micron cladding and 250 micron pitch and 80 micron cladding with 250 micron pitch. For example, this is 125 micron cladding fiber and 80 micron cladding fibers. And the upper figure shows 80 micron cladding fiber. And the below figures shows 125 micron cladding fiber. And actually, pitch is 250 micron, and these fellows are intermatable each other. Also, we have 80 micron cladding in PM fiber, especially for the external laser applications. And this slide shows reduced clad fibers intermatability test. And this shows good results for 80 micron single mode fiber connection with conventional 12MT parallel. And this is a summary of reduced clad fiber options. We have a 1/16 in fiber for 125 micron, 200 and 250 micron pitch. And also we have reduced 80 micron cladding with 200 micron pitch. Also, this is 2x12 fibers, and for both 125 micron and 80 micron fibers. And also finally 2x16 fibers. Both options are available in the future. And finally, if we employ the 80 micron fiber with 165 micron pitch, we can design the single rod 24 fiber in the future. It means that in the future, 2x24 fiber connector will be available. And this slide is showing a summary. First, very small form factor connector like as MMC will be suitable for 402 terabit BPS or above optical switch box interface. Second, reduced cladding, that is 80 micron diameter fiber supports future high density silicon photonics chip. And third, fiber system from 80 micron to 125 micron can be seamlessly designed not only with SM single mode signal fiber, but also with PM light source fiber with 250 with 250 micron fiber pitch. And for more detail of MDC and MMC connector, you can access this our website. Thank you.
All right. Thank you, Terry, and thank you, Paul, for both excellent presentations. A lot to study there. So, as mentioned earlier, these presentations are available on the Kobo website now for your downloading, and this entire webcast will be available as a replay in about a week. So we have a few minutes left here in this hour for questions and answers. So I would encourage anyone who has a question, please use the Q&A function below, and I'll read those questions out anonymously. So to begin with, here's one for both of our presenters, and that's the question of, since our challenge really is the importance of bandwidth density, have either of you considered the use of multi-core fiber, which is starting to appear in the market? Paul?
Yeah, for Optec's point of view, we can work with any kind of fiber on the shuffles. Yeah, so the answer is yes in that sense. Yeah, so we're actually seeing some discussion around applying these multi-core fibers on the optical engines or any other kind of on the board chipsets. It can be applied in the shuffles in the future.
And Terry, does Fujikura work with multi-core fiber in this application?
Yes, recently we got some inquiries of multi-core fiber assemblies. So in the future, this technology will be employed, I believe.
Okay, all right, interesting. Multi-core fiber has seems a lot of potential. Paul, there's some questions for you, so maybe we're going to need to see your slide deck again if you can share it. But the first question is, what is it that you meant by polarity, and what is the challenge with polarity that led Optec to make their own equipment to control?
So on this slide, we're showing 3 different kind of fiber shuffles. Yeah, so in the middle, this is the box type where the fibers are cross over each other inside. Yeah, and at the output, we can check just from the one end to the others. Yeah, so it's very important that all the fibers are laid correctly inside the box and exit correctly. Yeah, so with that, the manufacturing process would help a lot. And yeah, so let me bring down to, yep. So we have developed this semi-automated machine to help with the fiber routing, where this laser beam can direct from NA to NB. Yeah, so we can make sure that's channeled correctly. On the thin film fiber shuffles, this is already automated. So this is less concerned about the routings. Hopefully that explains.
Okay, very good. Will the fiber shuffle be required solder reflow for the survival in the future, or does it have it?
Yeah, let me go back to, here. Yeah, so the fiber shuffle, the scenario we are talking here right now is on the mid-board. Yeah, typically we're seeing the passive here. So what we learned from the industry is about where the reflow is used is the chipset fabrication. Yeah, so it is separated. Yeah, so we can actually load these passive fiber shuffles before or after the process of assembling these ASICs in the PCB boards. Yeah, so There's the reflow in this scenario is not required.
Okay. Excellent. Could you go to slide 14 as well? I think that's the prototype that you showed at ECOC in October.
Yeah.
Yeah, and so this one, I had a question that maybe you could explain a little bit more, because you talked about airflow and surface mount and the rest. So is this actually sitting above the PCB, or is sitting alongside of PCB? And how does that not interfere with the airflow through the chassis?
Okay. So again, this is just a demo. We are making this PCB or the flexi circuit fabric, just to demonstrate how the fibers can be laid. So about the airflow, the idea is to have a flushed surface. So the airflow, if we are coming from left to right, or if we are going from back to front, the high raised components does not intervene the airflow. So that's the idea of the flexi circuit.
Finally, I'd like to go back, Paul, if you still have your slides available, to your last slide, which was the solution to the riddle. I like that challenge a lot. So what you gave us was the challenge of just connecting three points with three endpoints, but really the challenge for these switches is much more complicated than that, right? 1024.
Yes.
Yes. The real challenge should be, how do you connect 1024 ports? But with you're allowed to do multiple layers.
Right. Yes, and it can actually allow cross lines on our shuffles. But with the minimum amount of that.
Okay. Well, thank you very much for that riddle. Thank you for the presentation. Thank you, Terry, also for your presentation. We learned a lot here in this session. So with that, we have finished the top of the hour. So wanted to thank our audience as well, and those who submitted questions, and especially thank you to the DuPont Silicon Valley Technology Center, which has been the sponsor of this series. So thank you everyone for joining today. And with that, we will end our webinar. Thank you.